Hello everyone, I am Ritobrata from INYAS-Mohali and today I'll be talking about one of my PhD projects. With the paradigm shift of human interactions to digital platforms, everyone is now familiar with the terms organic LEDs, organic field effect transistors and organic photovoltaics. And organic charge transport layer, among many other layers, plays a key role in fabricating such devices. The major bottleneck of the fabrication process, however, is faced during a solution processable method known as spin coating. If we take in solution highly crystalline materials, they are very good charge transporters, but they're fragile and rigid and their film will not be smooth and we will have pinholes and defects. But if we take fluidic materials, they won't be good charge transporters. So what to do? Here we bring in liquid crystals into the system. They are an intermediate soft state of matter, simultaneously possessing the order of crystals and the fluidity of liquids. They can self-assemble from their molten state and they can perfectly provide the balance between the extraction and transport of charge carriers as well as a uniform film formation. Thus, armed with these two superpowers, self-assembly and self-healing in films, we introduce disc-shaped or discotic liquid crystals to address these existing challenges. In our approach, we designed a molecule with a rigid pyrene core and flexible alkyl chains in the periphery. This R stands for the long alkyl chains. So if we take each molecule as a disk and one disk stacks on top of the other through the pi-pi interactions, they will form columns. And if charge is injected into this column, charge hopping will take place through the cores, which is denoted by the yellow part. And if this column arranges further into a 2D lattice, the orange part indicates the insulating sheath of the hydrophobic alkyl chains. So we will have a unidimensional charge transport in the system. And how do we prove it? Through polarizing optical microscope, where this birefringence pattern declares the anisotropy of a columnar structure. Also, we can do it by X-ray scattering, where we get the corresponding peak of each interaction and reconstruct an electron density map which shows us a columnar hexagonal lattice. Also, upon detailed photophysical studies in different solvents, we found out that our liquid crystal molecule was showing solvatochromism and also a hybrid local and charge transfer state upon excitation that lowers the reorganization energy of the molecule and facilitates a much faster charge hopping. As you see both from POM and SEM images, the nanofilms are perfectly smooth and defect-free. Then we fabricated devices using silver and ITO electrodes. We also tried doping with conventional inorganic dopants, but as you see, the order of conductivity is same with and without dopant, suggesting that the charge extraction and transport is the inherent property of our LCs. And also from the current voltage curves, the whole mobility is comparable to the existing organic semiconductors. So what is the take-home message? LCs can provide an all-new outlook in the field of flexible organic semiconductors and could be the futuristic organic charge transport materials. Our work was published this year in Small and also selected for the frontispiece. Finally, the field is at its infancy and we still have a long way to go. Thank you.